Hello everyone, this is our paper with the title Density-Aware Cooperative Precoding Technique for Massive MIMO Systems. I'm Shan Kochra from Hausa University, Dr. Alam Nagash, and Dr. Yeno Wande from Addis Ababa Institute of Technology, Dr. Faisal Dabo, Professor Raja Birappa are from Adama Science and Technology University, and Abraham Fakadu from USA. These are the outlines, the background about massive MIMO systems and precoding techniques, why we are motivated to work on this area, the objectives, subset of the arts and literature surveys, the methodologies through which we can achieve the desired objectives, how to calculate some capacity and energy efficiency by the aid of these precoders, and finally we'll be discussing the results and draw the conclusion. Massive MIMO system is a variant of multi-user MIMO in which hundreds and thousands of antennas can be installed on a single base station serving large number of users with the same time and frequency resource. In this case, the number of antennas to be installed on a single base station should be much greater than the number of users, and those users should have only a single antenna for each. One of the massive MIMO features are channel hardening, which is the property of massive MIMO to impact the problem of small-scale fading. And the next one is the favorable propagation condition, in which each and every subcarriers will be orthogonal to one another, and so that interference will be automatically suppressed and energy and spectral efficiency will be increased. So as the number of antennas increase in any massive MIMO systems, there are some problems which are related to those numbers. The first one is the pilot contamination, which arises from the pilot signals coming from different cells or neighboring cells. The other is the power consumption, which is related to those radio frequency chain components which are associated with those number of antennas. And as the number of antennas increases, the power consumption due to those radio frequency chain components also increases. And therefore, the system becomes costly. So as the number of antennas increases also, as the number of antenna increase, the complexity of the system due to channel estimation also increases as the detection or as the transmission. And again, array calibration, which is related to the placement of those miniature antennas, is also one of the problem of massive MIMO, and which is directly related to still the number of the antennas. So in order to avoid or resolve those problems, one of the salient feature is applying the precoding or beamforming techniques. And applying beamforming techniques in massive MIMO system is used to increase the capacity or the energy efficiency of the system. So before going to the detail of those types of precoding techniques, we'll be explaining the difference between, or the slight difference between the precoding and the beamforming. What we mean by beamforming, simply focusing the signal to the desired direction of the user, and whereas precoding means just coding of the signal and associating that code with some power allocation and the desired direction of the users. And in short, precoding or beamforming is subset of the precoding, and most of the time precoding is directly associated with those digital beamformings, and simply beamforming means mostly the same to those analog beamformers which focus the signal to the desired direction of the users by tilting the signal by using those phase shifters with time division duplex taken. So in our case, we'll be considering two types of precoding techniques. The first one is the linear precoding, like zero forcing, marginal ratio transmitter, and minimum mu-square errors. These precoders are also used to suppress the interference coming from those large number of users. And again, we'll be considering dirty paper precoding technique from nonlinear, which suppresses the causal and non-causal interferences and known for its higher capacity. So the motivation behind this work is, as we said so far, as the number of antennas increases, the size of the device also becomes smaller, and the wavelength also becomes smaller. And as the proximity of the users increases and the wavelengths of the users decrease, the complexity to the number of elements and the nature of frequency, so the complexity increases. And the other problem which is related to this large number of antennas in massive MIMO system is the interference arising from different directions due to large number of users to be employed at a time. So in order to avoid this complexity problem and the interference, we'll be considering, and so many researchers have considered those beamforming techniques like dirty paper coding from nonlinear and zero forcing precoders for linear. Even though this dirty paper coding and zero forcing precoders are known to suppress interference, and there are solutions for those complexities by grouping users or different techniques, there are still some gaps in applying dirty paper coding in the case of successive interference cancellation as a detection, which creates detection complexity. So when you apply this dirty paper coding, there must be a solution with detection complexity, which is still a problem of this precoder. And again, even though this zero forcing precoder from linear part is known to suppress the interference, the whole interference coming from different directions, there is another cause which is related to this precoder. That's the additional power consumption for diagonalizing the elements among the matrix. And therefore, it creates some inefficiency in the system compared to dirty paper coding. So considering dirty paper coding and zero forcing, they both have their own advantages and their own curses. And in our next step, we'll be considering how to resolve those problems among each and every precoders. So our general objective is to evaluate some rate and energy efficiency of cooperatively working these precoding techniques, particularly this dirty paper coding and zero forcing precoders will be combined together or work one after the other, depending on some parameters we will be considering in the next section. So to achieve this general objective, we'll be grouping the users within the cell, within the large cell or the cluster cell. We'll be evaluating linear and nonlinear precoders to know or to identify which is better, and to compute instantaneous density of the sector cells, since we are our basis is the density which is used to calculate the complexity of the system, and based on that complexity, we can switch back and forth to zero forcing or dirty paper coding. So it's must to first consider the instantaneous density and threshold density of the system. So finally, we'll be considering this density and complexity to evaluate energy efficiency and capacity or spectral efficiency of the system. So we have gone through different previously conducted research under research number 11, reference number 11. The authors have considered hybrid dirty paper coding with zero forcing to enhance total sum rate, and they have compared their work with the previous works, but still we found the gap of the power penalty which arises due to implementation of zero forcing, and that's what they could consider. And in next reference 15 to 20, the authors tried to minimize successive interference cancellation to increase the capacity by using hybrid dirty paper coding and zero forcing, even though they didn't consider complexity issue during detection as a receiver. And again, the authors under reference number 21 to 23 tried to enhance the total rate by using channel state information as a transceiver. And however, they didn't consider any results which have been conducted in previous works. And therefore, our system model to achieve the desired objective as looks like this. We considered a single base station with m number of antennas. In fact, this number of antennas can be any number, but in our particular case, we considered from 64 to hundreds and thousands. But in massive MIMO protocol, the number of antennas and the massive MIMO protocol can work with any number of antennas, but the number of antennas only should be greater than the number of usual terminals, and it can work in all frequencies, either with sub-6 gigahertz or millimeter wave frequencies. And again, we sectored the larger cell into different 3 regions, and we only consider the base station part, which is what we call the downlink part. And to achieve the desired objective, we have assumed some parameters like maximum cell range, operating frequency, which is some millimeter range frequencies, and the transmit power for the base station. And then we consider randomly generated users, and by splitting the cell into 3 regions, and after splitting the cell, we count the number of users in each cell by using uplink sounding signal and channel downlink channel state information, just to know the exact number of the user and the location of the user, in order in such a way that we can count and find the exact number of the users within the cell. So if there is no any user within the cell or a specific cell, then we can reiterate to counting the users and find the number of users with the same procedure. And if there is some users entered to the cell, we can calculate the specific density, and we can compare the specific density with threshold density, which is found through the maximum range of the cell and maximum number of users to be accommodated by the cell. So if the specific density is greater than the threshold density, then we can say the system is complex, and for this complex system, we simply employ the zero forcing than the dirty paper coding, since dirty paper coding by its nature has its no complexity issue, which operates with successive interference cancellation. And if this condition is not satisfied, or if the system is not complex, or if the specific density is less than the threshold density, we can simply apply dirty paper coding, and the base station simply transmits continuously and unless otherwise, the base station is put to some sleep or down state, it continuously transmits. So based on this proposed algorithm, we have compared the marginal ratio transmitter and zero forcing precoder for some fixed transmit power. So as the number of antenna increases, the energy efficiency of the system for marginal ratio and zero forcing also increase, but after some number of antennas, the graph starts to decline due to the reason that the effect of the number of antennas on total power consumption exceeds the effect of the number of antennas on the capacity. The same is true for spectral efficiency, that if we consider the zero forcing and marginal ratio transmitter for smaller number of antennas, marginal ratio transmitter for any fixed transmit power is better than zero forcing, and as the number of antennas increase, zero forcing becomes better than marginal ratio transmitter for any fixed transmit power. And if we simply consider the spectral efficiency only with zero forcing transmitter, then as we step from the bandwidth from 200 to 400, for the larger bandwidth, the spectral efficiency becomes lesser than the precoder with the smaller bandwidth, since the spectral efficiency is calculated through the capacity over bandwidth. So as the bandwidth increases, the spectral efficiency decreases. So the same is, we have followed the same procedure for this also, and for all number of antennas, as long as we are not considering the interference, or as we are suppressing the interference for the whole number of antennas. So as the number of antenna increases, the sum rate increases for the whole region logarithmically, and with the same procedure for smaller number of antennas, marginal ratio transmitter is better than zero forcing, and as the number of antenna increase, or for larger number of antennas, zero forcing will be better than that of marginal ratio transmitter. So in this case, we compared the dirty paper coding, regularized zero forcing and non-regularized zero forcing from perspective of total rate and signal to noise ratio. And for smaller signal to noise ratio values, non-regularized zero forcing is better than regularized, and for larger values of SNR, regularized zero forcing is found to be better than that of non-regularized. And for all cases, dirty paper coding for all SNR values, dirty paper coding is found to be better than the other two precoding techniques. And in this case, we have evaluated the total rate versus signal to noise ratio with proposed regularized, proposed cooperatively working dirty paper coding and zero forcing, and the regularized zero forcing, or cooperatively working dirty paper coding and zero forcing with some power penalty of zero forcing for the cell of 5 kilometer cell range. And we have found that our proposed algorithm is better than that of hybrid precoder with zero forcing with power penalty. In this case, the slight difference is only the cell range, and what we can say here is, as the cell range becomes smaller and smaller, the frequency also becomes smaller, and the frequency becomes higher, and the wavelengths becomes smaller and smaller, and so that the signal blockage increases with the increase in frequency. and so that for the same SN value compared to the previous one, the total rate becomes smaller and smaller. And in both cases, our proposed algorithm, the cooperatively working dirty paper coding and zero forcing, becomes better than that of hybridized dirty paper coding and zero forcing, or regularized or cooperatively working dirty paper coding and zero forcing with some loss of zero forcing, which is what seen with green color here. So in conclusion, we have investigated a large MIMO system based on millimeter wave, in which we considered only some range of frequency as operating frequencies with cooperatively working precoders. And we have also evaluated the performance of zero forcing and marginal ratio precoders with different users and different signal to noise ratio values. And we have also computed the complexity of the system by sectorizing the larger cell into different cells. And finally, we have found that our cooperatively working precoding, which is achieved through our proposed algorithm, has been found to be better than the zero forcing or dirty paper coding, which are working exclusively. And we have found that our proposed algorithm is better than the typically hybrid precoders with a power penalty of zero forcing precoders. Thank you for watching.